This is video 3 in the set of videos on the damped harmonic oscillator. So in this video we're going to look at an underdamped system. So we have a spring and we have a mass, and the mass sits in a viscous fluid and the spring is attached to a fixed point at one end. Okay, so in this instance here we've already found the roots of the equation. So if we imagine the roots of this equation are going to be b squared minus a squared less than 0. Okay, so that's the third option that we have. So in that case we could say b is less than our value a. So again, from the toolbox, well, what's going to happen then is we're going to have our m1 and m2. So m1 and m2 are going to be the complex conjugates. So you're going to have minus b plus or minus I times alpha. Okay, so where alpha is going to equal our value of root of a squared minus b squared. Okay, so again, if you look at the previous videos, you'll see where we got that from. We've been through the whole derivation in order to find a auxiliary equation and then a general solution for the damped harmonic oscillator. We're putting in our different values for our B and our A, which are directly related to, B is directly related to the viscosity of the fluid, and A is directly related to the springiness of the spring, okay, the K factor of the spring. Okay, and so if you're unsure about this and you just come straight in here, I would suggest you look at the previous two videos in order to get yourself up to speed with what we have here at the moment. Okay, so that there is the values for our M1 and M2. So the general solution for this equation here is going to be of the form x equals e to the minus bt, and again I'll do a playlist on solutions of differential equations. Okay, so we're just accepting these at the moment as just part of our toolbox of differential equation solutions. Okay, so it's going to be of this form: c1 cos alpha t plus c2 sin alpha t. Okay, so the initial conditions again. Initial conditions are of the form, well, at t equals 0, we have an equilibrium point at x0, and at equilibrium there's no movement in the system, so the rate of change of the positions with respect to time is going to equal 0. Okay, so we can find these we're looking for the values of c1 and c2. So initially when t equals 0, well, when t equals 0, sine of 0 is 0, so that disappears. Cos of 0 will be 1, so that will be a value c1, and this e to minus bt, it will be a value of 1, and the x will equal x0. So in that instance here, then we can just say x0 is going to equal a value of c1. Okay, now the second part of that, we've got to differentiate this here. Okay, so we're just going to have to use the product rule for differentiation, because it's going to be that times that and that times that, so you're going to end up with 1, 2, 3, 4 terms. Okay, so if we take out the common factor, the constant here, the first term, okay, so the constant first term is going to be c1, so we can take the c1 out and then we can differentiate the first term, so we're going to end up with minus be to the minus bt and multiply it by the other factor, which is cos alpha t, and then if we differentiate cos we get minus sine, so we're going to end up with our minus, and we'll multiply it by we're going to be the alpha, it's going to be e to the minus bt times sine alpha t. Okay, so all we've done is differentiate the cos, so we get alpha sine alpha t, so it's minus alpha sine alpha t. Okay, so that's the alpha come out, that's the minus sign, and then we multiply it by e to the minus bt. Okay, so that's just the product rule for differentiation. Okay, so that's two terms there, so that's one term there and a second term there, and the other part is going to be this differentiation here. So we're going to have take our c2 out, and we're going to have again minus b e to the minus bt, and it's going to be times our sine alpha t. Okay, and there's an alpha there as well. We've got that right. Yeah, there's an alpha going to be there as well. Okay, it's not alpha because we're not differentiating that. Okay, nonsense. Okay, so that's okay. So we've differentiated the first term, e to minus bt, and multiplied it by the second term here. Now we're going to differentiate the second term, multiply it with the first term. So differentiate sine, and we get cos, and we have the alpha value as well. So you're going to have the plus alpha e to the minus beta t times our value cos alpha t. Okay, so that's those other two terms there, one and two terms there. So all we've got to do is put in our values for dx by dt equals 0 when t equals 0. Okay, so it means that at t equals 0, well, we're going to have e to minus bt, that's going to be equal to 1. Okay, and when t equals 0, cos of that's going to be 1 as well. So you're going to have c1 times our minus b. Okay, this term here, when t equals 0, sine of 0 is 0, that term just disappears altogether. And the second term here, we're going to have our when t equals 0, sine alpha t is 0, so that term disappears altogether. And this sign here, cos alpha t will be when t is 0, cos of 0 is 1, and this term here will give us 1 as well. So we're just going to have our plus c2 times a value of alpha, and now we're saying that dx by dt is equal to 0 at that point there. Okay, so it means that you can rewrite that out and say that let's see, you could say minus c2 alpha equals c1 times b. Okay, but we already know that c1 is equal to x0, so that's actually equal to x0 times b. Okay, so we can put all that back into the equation above here for our c1 and our c2, because we've got our c1 is x0, and our c2 is x0 times b. Okay, so we put that back in, and we end up with x equals e to the minus bt times, we're going to have our x0 cos alpha t plus x0 b upon alpha sine alpha t. Now we can move the values out, so we can then say x equals, so we could take our x0 out, we can take the alpha out, and we're going to have a value of e to the minus beta t, and what's inside the bracket is going to be, well, we're going to have our alpha cos alpha t. So let's have a look and see. Yeah, we had to multiply that by an alpha because we've taken a divided by an alpha here, so we're going to have an alpha cos alpha t plus b times sine alpha t. Okay, now a little bit of kind of jiggery pokery here. If you say that a value, we say theta is equal to our inverse tan B upon alpha, then we can write the above equation in a more useful form. So we'll still have our x naught, and we'll still have our value of alpha, and we'll still have our value of e to the minus bt, still be the same, but what we can do is we write it in terms of just the cosine factor here. So you're going to have cos alpha t, and it will be minus some angle theta, okay, and we're going to be left with our magnitude, which is just going to be the root over a squared plus b squared, okay, sorry, a squared, it's going to be alpha squared. Change that and make these wee mistakes. Going to be our alpha squared plus beta squared. So all we've done really is put it in terms of, this is going to be our alpha and that's beta. So this tan theta is inverse tan beta upon alpha, b upon alpha. Okay, so theta is inverse tan b upon a. Okay, so it means that the actual length here, we're writing in terms of that length here, is going to be alpha squared plus beta squared root, okay, which gives us in terms of this distance here, okay, and it means we can just write it in terms of that distance there and a phase angle. So the phase angle there is just going to be this angle theta, okay, so just a standard way of manipulating the equation, okay. So that there then is the final equation that we're looking for, which is the equation for a critically damped harmonic oscillator. Now what we'll do is we'll have a wee look at that in our graphical calculator. So if I get into graphical calculator, we'll just quickly see all of these terms and you'll see exactly what they do. Okay, so there we have our equation here. Let's see if you can see the whole thing. Equation is here. So equation is our x naught upon alpha and our a squared plus b squared. So I've just called it a and b in this term. A squared plus b squared to the power of half e to the minus b times x cos alpha x, and the angle theta I've actually put in as a d because it wouldn't accept the theta. Alpha minus d. Okay, so let's have a look at each of these in terms and in turn. Okay, and again we can got our value of alpha there as well. Okay, so let's have a look at these in turn. So the value of d is just going to add phase on. Okay, so you can see that there. The graph remains exactly the same. It just shifts it along the x-axis. Okay, so we're just shifting along the x-axis. So that's just adding our phase term theta, or in this instance it's d. Okay, x naught is the initial starting position, so it's the maximum displacement of the mass. Okay, so I can adjust that. You can see it getting bigger and you can see it getting smaller. Okay, so that's just the displacement. Now the value of b, as we said, would be the value of the viscosity, and the value of a is directly proportional to the stiffness. So we can adjust the viscosity and the stiffness of the system. So watch the viscosity changes in relation to the stiffness, then you can see that the actual damping changes. So you can see that it settles down after only just as a value of b increases, it settles down after just one oscillation. But if we decrease that, or we change that value in comparison to the value a, then it goes through a lot more oscillations over a lot longer time before the system settles down. Okay, and again you can adjust the value of a. Okay, so when you adjust the value of a, you can see that the actual natural frequency of this system here changes. Okay, so you can see it, the crossover points here starting to widen out or narrow depending on the value of A. Okay, and I've just stuck in the envelopes here as well. Okay, so what we can do is I can play each of these individually, so you can see there's the value of D, which is just the phase of the system changing. Okay, so I can change the phase of the system, or I can change the initial displacement. So there's the initial displacement changing. Okay, and I can also change the factor of B, okay, which is directly related to the viscosity of the fluid, which the mass is going to move in. Okay, and you can see the damping changing there. If I just pause that there, I can also look at the value of A, which is going to be the stiffness of the spring, and you can see the natural frequency of the system changing. Okay, so I could change all of them at the same time. I suppose let's have a wee run through. There's B and A changing at the same time. Okay, I don't know what the value in is, but I thought I'll show you anyway. I could change the height as well, and also I could change the frequency, so there you can see all of them running together. Okay, so that just shows you the different scenarios for the damping factors for an underdamped oscillator. Okay, so that's all for this, and the next video we'll go on and we'll look at probably the wave equation. Okay, so thank you for listening and goodbye.